This video is going to explore the alkylation of the alpha proton. So the alpha position, as we've been discussing, is on either side, immediately on either side of a carbonyl carbon. We know that those protons are especially acidic for CH2 protons because of the stability offered to the lone pair when those protons are pulled off through resonance. And we've talked about the tautomerization of that anion, creating that enolate anion that acts as a good nucleophile. So step one in this reaction, LDA is the strong base that will deprotonate one of those protons, and then we introduce an alkyl halide. Whatever the alkyl group is what will be attaching on our alpha position, and of course the halogen is just acting as a good leaving group. So ultimately, the alkyl halide is acting as an electrophile, and our enolate, that's a result of the reaction number one, will serve as the nucleophile. We can see that mechanism down here. We have effectively a nucleophilic attack that's being illustrated with the lone pair attacking the R group, and then of course it's a loss of leaving group that we see when the halogen comes off of the alkyl halide. This is an SN2 reaction, and don't forget all of the stereochemical consequences of SN2, such as a backside attack, which results in inversion of stereochemistry if you're given stereochemistry for the alkyl halide. If a secondary or tertiary alkyl halide is used, the enolate, remember that carbanion that we just saw, let's flip back there. This is also, we know nucleophiles can also be strong bases. Good nucleophiles can also be strong bases. So when we aren't using a primary alkyl halide and we're using a secondary or tertiary, a bulkier alkyl halide, we'll often see that enolate act as a base instead of a nucleophile and do an elimination in that concerted E2 mechanism that we reviewed back in Organic 1. If you want to, you can practice doing an E2 mechanism using an enolate as a base. That would be a really great review getting ready for our final exam. When we are creating enols, of course, we know that the aldol reaction will be competing. So as an enolate gets created, it could react with the aldehyde or ketone that it is derived from and form an aldol product. So in that is why we often see LDA used as the strong base, which pushes that reaction towards the products. It's driving that reaction towards the deprotonated enolate. Now, we were looking at a symmetrical ketone to begin with, so we didn't have to worry very much about regioselectivity. But when we're using asymmetric ketones, like the one at the bottom of this slide, we can have different regio products, so different regioisomers. Remember, regioisomer is just a fancy word for constitutional isomer. So this ketone also has two alpha positions, but the two alpha positions are not the same. The structure is not symmetric, and so we could we can call these our HA protons versus our HB proton, and we would be creating two different enolates depending upon whether we deprotonated one of the HAs or the HB. So the next few slides are going to discuss the regio consequences of deprotonating either one of these alpha carbons, and how we as designers of reactions can control which side of an asymmetrical ketone gets deprotonated. So I was just highlighting on our last slide where our two alpha positions are. We had called this HB, and then these two we had referenced as HA. So if we pull off an HB, or the HB, we create the product on the left, which is labeled the thermodynamic enolate. So this enolate is a more substituted double bond, a more substituted alkene when it's in that enol form, which means it's lower energy overall. And of course, if we remember from our Gen Chem review, the thermodynamic product should be the lowest energy. Deprotonating one of the HA protons will give us the product on the right, our kinetic enolate, which is less substituted. But if you're looking at your structure, your HAs are more readily available. They're not strictly hindered in any way. So it'd be a lot faster to deprotonate one of the HAs as opposed to deprotonating the HB. The kinetic enolate is higher energy because your enol or your enolate product is less substituted. So we have a nice energy diagram to remind us about kinetic versus thermodynamic products. So this is a bit exaggerated. The energy differences really aren't this significant, but it kind of drives home the point. Remember, your kinetic product will have the lowest activation energy, but that may mean that it is higher energy overall, whereas the thermodynamic product is always going to be the lowest energy product. Sometimes kinetic and thermodynamic products are the same, or the kinetically favored and the thermodynamically favored are the same. In this case, they aren't. And if you need to review over that, we did that back in Organic Chemistry 1, so look in some of our earlier chapters. I believe that's covered in Chapter 6 specifically within our Klein textbook. So we have kinetic product, we have thermodynamic product. They make two different regioisomers. We want to be able to control that. The reaction conditions that control that are which base you're using and what temperature the reaction is conducted at. So if you want to make the kinetic product, where you're creating the less substituted enolate, you would use LDA under cold temperatures. So here's our minus 78 degrees C that I had mentioned in an earlier video, and then introduce your alkyl halide. And of course, this is SN2, so we want it to be a primary alkyl halide ideally. If you want to make the thermodynamic product, which comes from the more substituted enolate, you will use sodium hydride. Remember, hydride, our H minus, is a base. We've seen that on and off throughout this semester, but our hydride is a base. It's just not quite as strong as LDA, and you don't need to chill the reaction as much. In fact, running it around room temperature here, I've got 25 degrees. That's suitable for encouraging the thermodynamic product. So if we're thinking in terms of overcoming that higher activation energy, heating the reaction up just by running it at 25 degrees C instead of keeping it so cold, will encourage more of that thermodynamic product to be created. All right, we have a practice problem. We've been given this pretty large structure, and we're told to make this using carbon fragments that have 5 carbons or less. So what that means is we need to break down this molecule in a way where every single one of our carbon-containing compounds has 5 or fewer carbons. So we know that we need to have an alpha position, and then by the looks of this, we're going to be doing an alkylation since we have so many R groups coming off. So we have an alpha position here, and then we have another alpha position on the other side of that carbonyl. The alpha position that has a lot more carbons coming off of it is the one on the left. So I think that's where we should draw our reaction happening, is at that alpha. We can call that alpha 1. and then the other one is alpha 2, because we're working within the constraints of having 5 carbons or less for each part of this reaction. So pretty much what that means is this should be our starting ketone. Okay, so remember in our enolate reactions, the enolate retains its original structure. So here's the alpha position that will be deprotonating in this reaction, and that will allow an enolate to form to do a nucleophilic attack on an alkyl halide. So step 1 would be introducing LDA, for instance. And then step 2, we would want to introduce an alkyl halide. Well, we have an alkyl halide, one that has 3 carbons and one that has 2 carbons. And if we're counting our starting ketone, just to double check, we have 1, 2, 3, 4, 5. So by breaking up our molecule in this way, our largest molecule has exactly 5 carbons. I'm going to write the reaction so that we are attaching our smaller alkyl group on first. So I'm going to use LDA to make the enolate, and then at the carbon that I just labeled as number 1. And then my second step is going to be introducing ethyl iodide. So that would attach on it. And in fact, if we want to draw what that product is, product after 2, that would look like this. So there's my alpha position that we're attaching things onto. And to make it look like the structure that we have drawn for us, here's what that product would look like. We have another hydrogen that we can deprotonate in step 3, once again using LDA. Step 4, we'll introduce another alkyl halide. It needs to have 3 carbons. So I'll do propyl bromide, and that will give us our final product. So if my product after reaction 2 looked like this, then step 4 adds 3 more carbons on to that alpha position. And here's the alpha position where the reaction was being done. So the next couple sets of reactions capitalize on alkylating the alpha position and doing a couple of subsequent reactions. So it's still alkylation, but the names of the reactions are a little different because there's extra steps in them. The first one is the malonic ester synthesis. Effectively, if you're trying to think of patterns to keep all of these different reactions straight, the malonic ester allows us to go from an alkyl halide to a carboxylic acid functional group that has 2 extra carbons. So here's our R that used to be in the alkyl halide, and then we have 2 more carbons on that final carboxylic acid product. Malonic ester synthesis starts with diethyl malonate. That's the bottom structure on the left-hand side of the slide. We have our esters here, and we talked about our esters with respect to Claisen condensation. So some of this mechanism is going to be very reminiscent of what we saw in the Claisen condensation video. We want to make sure that our base matches our OR groups on the malonate, and since this is diethyl malonate, it will be ethoxide as an anion to pull off that alpha proton to create the doubly stabilized enolate. And we've seen these doubly stabilized enolates before in some of our earlier videos. So now we have a stabilized carbanion, again, doubly stabilized enolate, ester enolate. Lots of ways to describe this. It's pretty stable, so it's relatively picky in terms of what it will react with. It's going to react with an alkyl halide. This is going to be, again, that nucleophilic attack followed by loss of leaving group. So that SN2 pattern for mechanism, and we'll put one alkyl group in that alpha position, in that doubly stabilized alpha position. So this is a diester product that now has an R group coming off of the alpha position. And if we remember back to our carboxylic acid derivatives, we know that we can hydrolyze our esters and effectively turn our esters back into carboxylic acids. So the first part of the malonic ester reaction is an SN2 mechanism to put an alkyl group on the alpha position, and then you hydrolyze the the esters to give you 2 carboxylic acids. So instead of having the OET, you end up with OHs. This can be done with acid, as I show here on the slide, or with base, and a lot of times you will see heat used in this process. So once we have our dicarboxylic acid, our molecule can do this reaction that we see here. This is a type of reaction that we're going to go back and cover in chapter 16 called a pericyclic reaction. And that's where bonds within a molecule react in a cyclic way to rearrange the molecule is one way to think about it. It involves breaking and forming new bonds. So what we see here is we've kind of taken advantage of free rotation and made it so that the hydrogen from one carboxylic acid is actually very close to the carbonyl of the other carboxylic acid on this diacid. We see the pi bond from the carbonyl attack that proton, and that's how we get our alcohol in the intermediate product. If we're doing that, then the electrons on the OH in the carboxylic acid that are holding the hydrogen onto the oxygen can go to create a double bond between the oxygen and the carboxylic acid. When it does that, this carbon right here will be overfilling its octet, and so your molecule will actually cleave a carbon-carbon bond and form a new double bond, and one oxygen, two oxygens, and one carbon will give us CO2. CO2, of course, is a gas, so this is going to be an irreversible reaction where the gas is bubbling up and out of the reaction, forcing the creation of this enol, which I know it has 2 alcohols on it, but it still has a double bond and an OH attached onto that carbon. That will go through a tautomerization, so enol is a good term. It's not really a keto-enol tautomerization. Instead, we end up with a carboxylic acid final product. Now, this is the end of that malonic ester synthesis. We said that we were adding on 2 carbons to an R group that originally came from an alkyl halide, and that's exactly what we've done. You may be thinking, why don't we see the second carboxylic acid also come off? Well, the decarboxylation is based around the fact that you have 2 carboxylic acids that can be arranged close to one another so that you can pull off one of the hydrogens and the CO2 can cleave off. Because we now only have 1 carboxylic acid, we no longer have the right molecule structure to encourage that pericyclic reaction that will yield CO2. So here's an overall synthesis example of the alkylation and the malonic ester synthesis. So once again, we know it's diethyl malonate because here's our diethoxymalonate because we've got this guy with the 1 alpha position. So our sodium ethoxide and ethanol. Ethanol, you want your solvent to match your OR groups on the esters as well to avoid that transesterification that we talked about in our Claisen reactions. But effectively, step 1 is going to be deprotonation. Step 2, introducing the alkyl halide. That's a primary alkyl halide, right? That's going to be our SN2. So our alkylation. And then step 3 is actually going to be hydrolysis plus our decarboxylation. We can also just write it as minus CO2. So the part that is highlighted in green here is the carboxylic acid, which originally came from the ester. And so we still see that that new bond was formed at the alpha position of the original ester. And of course, if we're continuing our numbering, I know that this isn't how we would number at all for nomenclature, but that carbon number 3 in this product chain is going to be that CH2 coming from our alkyl halide. We can do double alkylation using the malonic ester synthesis. So just like we saw in our example for alkylation, if we have 2 protons here, then we can certainly remove both of them. And so that's what we see here. This reaction should be very similar to look similar to the problem that we worked out together earlier in these slides. Step 1, notice the base matches our ester. Step 1 would be removing 1 proton. Step 2 is attaching 1 R group. So this is from step 2. Step 3 removes another proton, and step 4 attaches on the second R group there. This time, I went ahead and broke it up. We have our H3O plus for, again, hydrolysis to a carboxylic acid and our decarboxylation. So, once again, even though we have 2 carboxylic acids, this would give us a dicarboxylic acid that can then go through that pericyclic reaction to remove 1 of the carboxylic acids, leaving us with 2 carbons, and from the starting material, I've got my 1 and 2 carbons labeled to kind of illustrate that point, and then our alkyl halide R's are color coordinated with the alkyl halides over the arrow. And again, the only requirement for the alkyl halides would be ideally their primary alkyl halides to encourage substitution instead of elimination. Another alkylation reaction that can happen is this acetic ester synthesis. So it's a bit of a mouthful, but the mechanism of this is going to be very similar to what we had seen earlier with the malonic ester synthesis. Ultimately, the overall result of the reaction is taking an alkyl halide and attaching it on to effectively an acetone group. So here we've got our acetyl group. Here's another alpha position, and the alpha position is going to be where the R group from the alkyl halide attaches. So here's a reaction. I have a slide coming up that's just blank for you to be able to practice this. So the starting material for this acetoacetic acid ester synthesis is a beta-keto ester. So ester rather. So if we're looking, okay, we have our alpha position here and a beta position there. So there's our beta keto, okay? And of course, here's our ester, and then there's our beta keto, right? If you go back and look through the Claisen condensation slides, you'll see that your product of a Claisen condensation is actually a beta-keto ester. We may not have used that term, but this is effectively a Claisen condensation product. So once you do a Claisen condensation, you can follow it up with these new reaction conditions in order to ultimately create just a ketone. So let's go through what these steps are doing, and I'm going to end the slides on a blank slide deck, blank slide where you can practice drawing out the mechanism for this reaction. So step 1, again, we've got our matching ORs for our ester starting material for the beta-keto ester, as well as the base and the solvent. So this is, again, going to be deprotonating the alpha position, avoiding transesterification. Once we have the deprotonated alpha position, that's going to act as a good nucleophile and attack our primary alkyl halide via an SN2 mechanism. So that's going to be how we connect our benzyl group onto the alpha position of our beta-keto ester. So that's the alkylation part of this reaction. Step 3 serves two purposes, same as what we saw with malonic ester. We can do this under acidic or basic conditions. This is showing acidic, but first you're going to hydrolyze the ester, and then it's going to decarboxylate to get rid of the ester and leave us with just the ketone part of the starting beta-keto ester. So if we're counting carbons now, here's what came from the original beta-keto ester. And I'm going to go back and number those same carbons. And again, this isn't necessarily how it would get numbered for nomenclature, but that means in my numbering, carbon number 3 is the alpha position. And pretty much the theme of these acetoacetic acid synthesis is that your ketone will have just one methyl coming off of it so that you get that acetyl group on there. But yeah, this is basically a way where through 3 reactions, you can go from a beta-keto ester to what would be a beta-keto acid, where we have the carboxylic acid, and then decarboxylation will yield a ketone. Here's the blank slide if you want to pause the recording and practice drawing that mechanism. Make sure that you show your deprotonation step, and you can practice drawing the tautomerization of the, practice drawing the pericyclic reaction for that decarboxylation step at the end after the SN2 reaction.